So, as I mentioned earlier, the numerical integration, I mean the finite element operations have to be performed on digital computers, and integrations on digital computers over finite definite integrals over digital computers, they are approximation, they are called numerical quadrature, I mean quadrature schemes. So, analytical evaluation of integrals is very slow and not very often, and most of the time the, as we will see in our finite element formulation, it may not be possible to have analytical expression that can be integrated even with the symbolic computer system that is available, that might be available. So, it is not always possible to use analytical integration, and it is much more convenient and much more efficient to use numerical integration, and it can be it is very quick and very efficient and accurate enough for our purposes. And the way definite integrals are evaluated on a digital computers or using any quadrature rule, they are essentially based on weighted sum of function values. So, we have an integral, let us say integral that has to be f of x, that is the integrand, and that has to be evaluated integrated between the range a to b. So, that integral is evaluated as a weighted sum of function values. Function f is evaluated at several points x I in the range a to b, and there are some weights assigned based on the sampling points, and those weights are multiplied with the function values at the points, and then they are added up, and this particular summation, weighted summation, is taken as an approximation of the definite integral. And simple enough, as you can see, it is only accumulation, addition is the simplest operation on a digital computer. So, it is a very simple scheme per se, and the objective is to compute the weighted sum such that the error is under certain specified threshold. So, the weighted sum that we have is within certain tolerance level of the exact integral that we might be there for any function analytical expression. So, elementary graphical methods that we all studied of computing the areas under any curve. So, for example, rectangle rule or trapezoid rule, they are the good starting points for studying numerical quadrature. So, if we look at any any function, so any function, it can have variation, any arbitrary variation. So, we take the first on the left hand side is what we call as rectangle rule, on the right hand side we have what we call as trapezoid rule. So, in rectangle rule we find out the value of the function at the midpoint of the interval. So, x sub c, that is the centroid, that is the central point in this interval x I and x I plus 1. We find out the function value and assume that that constant function value is holds over the entire interval, and then we compute the area of rectangle. So, there will be some areas where it would be overestimated, and there would be some areas, some regions where it will be underestimated than the true sample. But if we take these intervals small enough, then it should average out and results should be satisfactory. In trapezoidal rule, we take the function values at the endpoints. So, if x I and x I plus 1, they are the sampling points. So, we just take the function values at x I and function value at x I plus 1, and then just use the area of trapezoid between these 2 points. So, and that is taken as an approximation. Now, both these methods, rectangle rule as well as trapezoidal rule, they are first order accurate, and uh, error decreases linearly as we uh, reduce the interval between adjacent points. So, rectangle rule, the coefficient here is the interval length of the interval h. So, for ith interval between x I and x I plus 1, if the interval is h I, then h I becomes the weighting coefficient, and the function is evaluated at the central point, center of this interval. So, that additional calculation needs to be done, and then obviously then it is simple addition of these function values, weighted sum of these function values at the middle of the interval. And trapezoid rule, it is the coefficient is of course h I by 2, and we take the two function values. So, essentially alternate we can just say we just trapezoidal rule. So, it is merely the average of the function values at the two endpoints and multiplied by the interval. So, that is the area of this trapezoid. Now, interestingly, if we try to figure out what is the error, then we find that trapezoid rule is actually more slightly incurs slightly higher error than rectangle rule. So, to analyze this problem, or to appreciate this problem, this particular fact, let us try to find out, I mean both of them will integrate a straight line exactly, rectangle rule as well as trapezoid rule. So, the approximation, the error will be incurred only when we try to integrate a second degree polynomial by these two rules. So, let us try to integrate x square by using both of these rectangle rule and the trapezoid rule over the interval 0 to 1, just to serve as an example, some numbers to study. So, you can check it out. The error in integrating a quadratic by using trapezoid rule is 2 times that incurred using rectangle rule. Work it out and you will be surprised at this result, but interestingly the error is of opposite sign in both the methods, right, and therein lies opportunity. And this is what this is how numerical algorithms are, I mean the scope of improvement in numerical algorithms are detected. How do we make use of fundamental results, fundamental observations, and use that to our advantage. So, two basic first order methods have an error of the same order, they are first order accurate, but the error term is of opposite signs. So, that means if we can somehow add them together, then the error term will vanish, because the error is of opposite sign. So, and we know that error in trapezoid rule is 2 times that of the rectangle rule, right. So, if I use the rectangle rule and to double that and add it to the rectangle trapezoid rule, then the error term will vanish and I will get a higher degree of accuracy, and that is how Simpson rule is derived. Simpson's rule is derived from this observation and eliminating the error by a suitable combination of rectangle and trapezoid rules. So, I1, as you can recall, if you recall, I1 refers to rectangle rule and I2 refers to the trapezoid rule. So, 2/3 weightage is given to rectangle rule result and 1/3 weightage is given to trapezoid rule result, and resulting summation is familiar Simpson's rule, and that has a higher degree of accuracy, it is second order accurate. And further, if we go further in this context, then we can develop a series of formula, Newton-Cotes formula based on integration of Lagrange interpolation polynomials. So, we have these data points, sampling values, sampling points and the function values. So, if we do not have the analytical expression, then we can actually construct a Lagrangian interpolation, and once we have the Lagrangian interpolation, then the integral of Lagrangian interpolation, it is a well known function, and the integral can be evaluated and the data sets can be populated, and that is how the Newton-Cotes formulas are derived. So, that is the coefficients, weighting coefficients in the weighted sum, they are essentially the coefficients, the terms related to integration of Lagrangian interpolation polynomials between the range of integration. So, another topic, another interesting issue is these are all based on polynomial interpolation and very handy, but if I can approximate it well, polynomial interpolation is not very good at approximating the function over the entire range, as we have seen, but we have seen that cubic interpolation, cubic spline interpolation can be a very good, can provide a very good approximation to the function over a smaller range, and we can divide the range into smaller and smaller segments and construct cubic spline over smaller segments. Now, once we have the cubic splines, we have an analytical expression. So, we can simply integrate that cubic function that we have analytically over the individual subdomains, and we can get the results for numerical integration, definite integral over the certain range. So, the process obviously begins with construction of suitable cubic spline over smaller intervals, and then integrate those cubic polynomials analytically. So, nothing can possibly go wrong here. So, this is particularly attractive for integrating functions which are available only as a set of discrete samples. So, if the function values are only available as a set of ordered pair of points, then I can very easily construct cubic splines and then integrate the spline functions, cubic spline functions analytically over individual segments, and that can be taken as approximation for integrating over the tabulated set of data points, function defined by tabulated data points between certain range a to b. Now, all these functions that we have, all these numerical quadratures that we have used, that we have seen so far, the common theme is the integral, definite integral is replaced or is approximated by a weighted sum of functions, function values. So, function has to be evaluated at specified points unless it is given as a data pair, I mean numerically data pair that is already available, but if it is not available, it has to be evaluated at specific points, then that there is a cost involved, computational cost involved in computation in evaluating the function at specified points. Now, function evaluation is the most expensive operation in this whole process, because sometimes it is very complex function that needs to be evaluated. There are so many things that go on in evaluating the function, particularly in finite element approximation that we will develop. So, it is always worthwhile to explore which method or which integration method will provide sufficient accuracy with minimum number of function evaluations. And it so happens that Gauss-Legendre quadrature, as they are called, they are the optimal in terms of sampling required for integrating polynomials. So, as long as we are integrating polynomials and over a finite range, then there is the minimum number of function evaluations that we may need for a specified degree of accuracy. The Gaussian quadrature or Gauss-Legendre quadrature, as it is called, is the most efficient computing technique. So, what is done? I mean, obviously the basic form still remains the same. Function integral, definite integral is still evaluated as sum of weighted sum of functions, but what is done is the sampling points are determined based on the optimality criteria. So, we try to find out what is the most accurate approximation that can be constructed, most accurate evaluation of the integral for a given number of sampling points, and find out what should be the optimal location of those sampling points and associated with what should be the optimal weighting coefficient. So, both the combinations are left to the optimization process, the weighting coefficient as well as the sampling point. So, we try to find out what is the weighting coefficient and what is the corresponding sampling point to achieve the maximum accuracy in the numerical quadrature. So, the derivation is a little bit involved, so and not really worth spending time on it. What we really need is the result. So, the point is the sampling locations, it so happens that the optimal sampling locations, they correspond to the roots of orthogonal Legendre polynomials of required degree. So, very interesting. This theory of polynomials has a very interesting contributions to the numerical computations. So, as we saw, orthogonal roots of orthogonal Chebyshev polynomials giving us optimal locations for function polynomial interpolations. Now, we have roots of orthogonal Legendre polynomials, which would give the optimal locations for evaluation of numerical quadrature. So, a polynomial of 2n minus 1 degree can be exactly integrated by using an n point Gauss-Legendre quadrature. So, it is defined over interval of -1 to +1. So, any arbitrary interval can be mapped into this range and function values by suitable change of variables, and the integral is evaluated as I said by weighted sum of function values over the interval. So, n point integral, n point quadrature rule would have these n number of terms w I multiplied by function evaluated at xi I, xi being the sampling interval, sampling point location, which would correspond to the root of Legendre polynomial over the range -1 to +1. And for use with arbitrary limits, as I said, a linear transformation between the variables of integration can be imposed, so that integral between a to b can be mapped to integral between -1 to +1 with suitable change of variables. So, x can be mapped to normalized variable xi by suitable linear transformation. So, typically we have these sampling points and associated weights. So, number of function evaluation. So, if we have only one function evaluation, single point evaluation, then that corresponds to the midpoint of the domain, -1 and +1 is the range, and the weight is 2, and polynomial of 2n minus 1 can be exactly integrated. So, first degree polynomial can be exactly integrated, and as you can see, that corresponds to rectangle rule if you work this out, and Gaussian rectangle rule is can exactly integrate a first degree polynomial. If we go by two number of function evaluations, the sampling points are plus or minus plus 1 by root 3 and minus 1 by root 3, and the sampling weighting coefficient is unity. And for two number of function evaluation, the highest degree of polynomial that can be integrated exactly is 3. We can integrate cubic polynomial exactly by just two function evaluations. And if I go to function evaluations, 3 number of function evaluations, then I can integrate up to 5th degree polynomial exactly, right. And the sampling points are 0 with weight of 8 by 9 and plus or minus square root of 3 by 5 with the weight of 5 by 9, and so on. There are other points, other sampling intervals, but rarely we need to go beyond 3 point integration. In finite element approximation, we will rarely have need to go beyond 3 point function, 3 point quadrature rule. So, that actually suffices for all our practical purposes, but many books on numerical analysis will give you appropriate sampling points and weights for different orders of Gauss-Legendre quadrature that can be used for analysis and most efficient evaluation of numerical quadrature. Now, that was for one dimension when there was only one variable, independent variable. What to do in case of 2 dimensions or 3 dimensions? Our problems can be multidimensional. So, the new integration also has to be evaluated with respect to several dimensions. So, multidimensional, double integral and triple integrals. So, very easily extended, the general form is a multidimensional integral is just replaced by, each integral is replaced by a weighted sum. So, now we talk about if there are 3 dimensions, then there will be 3 sampling points, a ordered pair of 3 sampling points and associated with suitable weighting coefficients. So, a triple integral is replaced by a triple sum, approximated by a triple sum, and weights and the sampling points are chosen appropriately, just in the same way as in the case of one dimensional evaluation. So, with this we can compute the numerical integral as we may need during the process of our operations of finite element method formulation, and then that will set the stage for further calculations. So, with this we wrap up the basic introduction and basic tools that we may need for development of finite element approximation, and we will begin with discussion of finite element formulation from the next lecture. Thank you.